Okay, so we're going to continue on with the scatter plots and correlation. And we're going to do measuring the linear association, and that is the correlation, okay? The correlation is represented as R. If you remember when we were doing regression lines, there was, when you turn the diagnostics on or off, you got the R, and you also got something called the R squared, okay? We'll talk about the R squared in 3.2. Okay, right now we're going to talk about R, just the correlation. Okay, the correlation here, R. So correlation is a number that is between -1 and 1. Okay, positive and negative, right? Because there's a positive correlation and there's a negative correlation, right? Okay. So if you have a correlation that is R is equal to 1, that means that if you drew your line, every single point is going to be exactly on the line, no deviations, right? Okay, so it's exactly a line, linear relationship, right? Okay. So that would be one thing about the correlation. And what else does it say? Underneath the green box here, in the middle, there's a green box called the correlation R. The linear association between two quantitative variables, the correlation R measures the direction, strength of the association. Okay, so R is between -1 and 1. We'll talk about that. Correlation R indicates the direction of a linear correlation. Okay, the linear correlation. So we're only going to talk about correlations during a linear relationship, during a linear association. Okay. Also, let's see, third one, extreme values, -1 and 1 occur only in the case of a perfect line or perfect linear relationship. If the relationship is strong, the correlation R will be close to 1 or -1. If the linear relationship is weak, the correlation R will be close to 0. Okay. Underneath there is a red dot that says it is only appropriate to use the correlation to describe strength and direction for a linear relationship, okay? So whenever you're talking about correlation or an R value, you are always talking about a linear relationship, okay? Go to top of page 161. It gives you the examples of a strong and weak positive relationship, a correlation, and then you have a negative, weak and strong, right? And then you have the correlation R is equal to 0, where there is no relationship, okay? So let's flip the page, go to payroll and wins. Okay, this is a revisiting of the MLB wins versus payroll. The correlation factor there was 0.613. So that's why it was not necessarily a strong relationship, but it's not a really weak either. So it's, somewhere between there. The book says a 0.613 confirms that the linear relationship with the payroll number is moderately strong. Okay, so the book is calling it a moderately strong relationship. Okay. Okay, some important stuff. Go to top of page 163. Cautions about correlation. Okay, the most important one, the one that comes up on the test, on the AP Stats test, the most often is the one, the red dot there. Correlation does not imply causation. Okay, just because there's a tight correlation does not mean there's a cause and effect thing there going on, okay? Okay. So make sure you understand this. There are very, very few things where you can actually say there is causation. In order to create causation or to verify causation, we have to jump through a lot of hoops and a lot of things, a lot of boxes that need to be checked for a statistician to be able to say that there is causation. Okay, so most of the time, causation does not happen just by happenstance. Okay, so correlation does not imply causation. Flip the page. The second red one says, correlation does not measure form, okay? So correlation here, if you look at page 164, you have 1, 2, 3 separate things there, and the R is the same for all of those. Okay, so in other words, R does not mean automatically it's linear. Okay, so the correlation does not mean measure form. Here's so that's why on the second one it says what? Correlation should be only used to describe linear relationships. So that's why we're going to only use correlation in linear relationships. Top of page 165. Correlation is not a resistant measure of strength. In other words, correlation is very, very dependent or gets swayed by outliers. Okay? So, let's go to bottom of page 165. Nobel chocolate. Okay, most people love chocolate for its great taste, but it also will also make you smarter. A scatterplot like this one recently appeared in the New England Journal of Medicine. The explanatory variable is the chocolate consumption per person for a sample of countries. The response variable is a number of Nobel Prizes per 10 million residents in that country. Okay, if you look at the scatter plot, does it look like there is a linear relationship there? Does it look like the correlation is 0.791. So it's not only is there a linear relationship, but there's a pretty strong one, okay? Now this would be a typical where correlation does not mean causation, right? So A, flip the page. If people in the United US started eating more chocolate, could we expect more Nobel Prizes? Well, no, because just because you have it doesn't mean it's causation, right? B, what effect does Switzerland have on the correlation? Explain. Switzerland, so let's flip back. Where is Switzerland? Switzerland is way out there. They eat a lot of chocolate and they have lots of Nobel Prizes, okay? So it's basically so when Switzerland is included in the rest of the points, it makes the association stronger because it doesn't vary much from the linear pattern. Okay, it makes the correlation closer to one. In other words, it dictates a lot of things what happens, okay? Okay, so moving on, it says calculating correlation. So how do you actually calculate correlation? Let's look at the green box there, and it is going to be, this is how you calculate the correlation, okay? You have x of I, x bar over x, y I minus y bar over y x. Okay, it looks pretty daunting here. So let's take a look at what we have here. What do we have here? So for every I, right, is equal to 1 through n, okay? For every I, you're going to go x of I minus the mean divided by the standard deviation, okay? Well, this guy looks familiar, right? What is this called?
The Z-score.
Anybody remember what this is called?
The Z-score?
This is the Z-score. So this is the Z-score in the X, right? For the X, right? Whereas this guy is the Y Z-score, right? Yi minus that divided by the standard deviation, right? So basically what you're doing is you're taking for every point, you're going to calculate the Z-score in the X direction and the Y direction, and you're going to multiply those two Z-scores together. And for every point, you're going to multiply those two together, then you're going to add all of those, right? You're taking the sigma, you're taking the sum of those multiplications, you divide it by 1 minus n, Okay, so you're averaging that to a certain point, right? If it was a true average, it would be this, but there's a reason why, because we use n-1, we do 1 degree off, okay? And the reason why that we do that is not applicable for this class, so we're not gonna go there. But just remember, so it's the x-score times the, it says z-scores of in the x and the y direction. You're gonna multiply those two together, you're gonna add those all, and then you're gonna kind of average that. That is how you calculate the correlation. Okay, you're never going to be asked to hand calculate the correlation. Okay, not only that, I believe this is also in your cheat sheet, so you don't have to really memorize it. Okay, but just realize that this is how this is done. Okay, so if you flip the page, go to page 168, there are some additional facts about correlation. Okay, number one, correlation requires both variables to be quantitative, right? Obviously, you cannot have a linear relationship or whatever between if they are not quantitative variables, if they're categorical values, right? You don't have these numbers, right? Okay, because you're gonna have what? In categorical values, you have what? You have proportions, right? You have P's, right? There are no P's here, okay? All right. So number two, correlation makes no distinction between explanatory and response variables, right? Because in here, this is the explanatory variable and this is the response variable, right? If you switch the explanatory variable and the response variable, it doesn't matter because you're multiplying the two together anyway. Right? It doesn't matter which one you multiply first, right? It's the same. So it doesn't matter which one you call the explanatory value or which one you call the response value as far as the correlation is concerned. The correlation will still be the same, okay? And then number three, because R uses the standardized values of observation, R does not change when we change the units of measurement, right? Because you can change the units of measurement all you want. If this is going to be in millimeters and this is millimeters, it cancels out, right? If this is centimeters, this will be in centimeters also, so it cancels out, right? So it doesn't matter what unit you are in. Even if you do inches versus inches and you had it in centimeters, whatever correction factor you make is going to be applied for the top and bottom, okay? And also, then that's what it's called, why it's called standardized, right? Because it does not need a unit. Okay, it doesn't have a unit. Okay. Fourth one, the correlation R has no unit of measurement. It's just a number, right? Again, inches over inches cancels out. There's no unit. There's no unit here. So it's unitless number times a unitless number divided by just a number, right? There is no unit to this. There's just number of observations, right? So if I had 10 points of observation, this is just going to be 1 over 9. And so there's no unit. So therefore, there is no unit for the whole thing. Okay, let's go to the example long strides. Let's look at long strides here. It says problem. The following scatter plot shows the height in inches and number of steps needed for a random sample of 36 students to walk the length of a school hallway. Okay. The correlation is negative 6.32. Okay. Does this make sense? Anybody? Does it make sense that you have a negative value there? What can you say about the 1 foot or 1 length, right? Or 1 footstep? How large or how wide it's going to be versus height. Can we generalize and say that the taller you are, the longer each 1 footstep is going to be? Does that make sense? And therefore you will be taking less strides in the hallway, right? So therefore, yeah, it makes sense it's a negative, right? A, explain why it is incorrect to say the correlation is negative 6.32 steps per inch. Okay. Well, correlation is just a relationship, right? It doesn't measure, there's no units to it, okay? All right. B, what would happen to the correlation if number of steps was used as the explanatory variable versus, and the height was used as a response variable instead of the way they have it down there, right? Because the initial scatter plot had the height being the explanatory variable and the number of steps being the response variable. Well, we just saw that it wouldn't change anything, right? So B, the correlation would be the same because the correlation doesn't make a distinction between the explanatory and response variables. Okay, that's good. C, what would happen to the correlation if the height was measured in centimeters instead of inches? Well, nothing would change, right? Because it's a standardized value, right? It's a unitless standardized value, right? So nothing would change. All right, we're done with 3.1. We're done with 3.1. Any questions there?